Hello everybody. Today we're going to work on taking the derivative using very simple power rule, sum, and difference rules. So let's get started. When you have an expression y equals 4x to the third, let's start there. The derivative of this, y prime, or some people prefer dy dx, the derivative of this will be by the power rule. Why? Well, there's a power. And how does one deal with the power rule? Well, the rule states, if you look on your formula sheets or you look in your calculus book, it states you should take the exponent, bring it down to multiply by the coefficient in front of the expression, so 4 times 3 to give me 12. And then, on top of it, you subtract 1 from the exponent, which should bring the exponent down to a 2. And this is our first derivative of the expression y equals 4x cubed. Again, this is by the power rule, which bring the power down to multiply, as I did, 4 times 3, and then subtract 1 from the exponent to give us x squared. By the way, sometimes you are asked to find the second derivative. The second derivative is the derivative of the first derivative. So really what we're going to do now is reapply the same exact rule. It's a power once again. So by the power rule, I'm going to bring the power down to multiply, and that gives us 24, because 12 times 2 is 24. You might want to have a basic calculator handy if needed. And then once again, we subtract 1 from the exponent to give us 1, because 2 minus 1 is 1. And so this is the basic power rule. We're going to be using this a lot today in a few examples that I have. So the first thing I want to talk about is if you have a function, an expression, a very simple one, could be simple as 4x squared plus 7x minus 10. And you want to take the derivative of this expression. Why do you want to take the derivative? Well, you can follow one of my future videos because you might be looking for a max or min, you might be looking for an instantaneous rate of change, or you could be looking for a slope of a tangent line. There are many, many applications, a marginal if you're doing it in business, there are many, many applications for the derivative. Please see future videos for this. What I'm teaching today is a review of the rules. So we have this nice rule that states if you have a combination of adding and subtracting, you are allowed to take the derivative of each little piece separate. And that's what I'm going to do here. And in fact, these to me are 3 separate expressions, 3 separate rules. You'll see this is nothing more than the one we just worked on. That is, we're going to bring the power down to multiply to make it 8, because 4 times 2 is 8. And then we're going to subtract 1 from the exponent to make it 8x to the first. Now we move on. The cool thing about 7x minus 10 is if you understand the derivative is the slope, if you just focus on 7x minus 10, 7x minus 10 is a line. The slope of a line, well, think of the equation of a line. It's mx plus b. In this case, the slope is played by the number 7. And that's why the derivative of 7x will always be the constant in front, in this case 7. And that's also why the derivative of a constant will be 0. Because if you look at the graph of a constant, just look at the graph of negative 10, that is a horizontal line. The slope of a horizontal line is 0. Hence, once again, the derivative is the slope, and that's why we get 0. Let's augment and go to 7x minus 10. 7x minus 10 is a good old line, mx plus b. The slope of this line is 7, and that's why the derivative of 7x is 7. The derivative via the power rule is a little bit more advanced. I'll let you look that up why it is. By the way, we should always try to do simple cleaning up. In this case, the simple cleaning up would be to get rid of the 0. And there is our first derivative, 8x plus 7. Awesome. So now there are 3 popular things that I need to make sure you're aware of when we take the first derivative. First and foremost, if you have a radical, for example, the square root of x. Now you can look up to see if there's square root rules. What I will be preaching in this video is all about recalling your exponent rules. So the square root of x actually can be written as x to an exponent. The question is what exponent? So you just gotta bring out your exponent rules and recall the square root is a 1/2 exponent. Now that it's just a good old power, you got it. I'm going to bring the power down. So 1/2 comes down in front. I'm going to subtract 1 from this. Whoops, didn't mean to write that. Let's get my eraser out. So we're going to subtract 1 from the exponent. 1/2 minus 1, again, if you need the calculator, 1/2 minus 1 is a negative 1/2. And there is my derivative. Typically, professors are going to want you to clean this up. And how do we clean this up? Well, a negative exponent means we actually can put that item into the denominator using exponent rules. A negative exponent really means to put the expression into the denominator. And so that's what I'm going to do here. I'm going to rewrite this as the following using an exponent rule. A negative exponent means the expression can reverse its position. It once was in the numerator, it's now going into the denominator as a positive exponent. Again, you have to review your rules of exponents to really be good at taking the derivative. Often, the derivative is nothing more than algebra rules. So being sharp with algebra is extremely important in this lesson. So we took care of a radical. Well, let's do another one just to make sure we're clear. Y equals, and it doesn't always have to be the variable x. I'm using x because of the technology I'm using. But let's say we have the cube root of t in case we're doing a time variable, whether it's physics or business example. We have the cube root of t. Well, once again, I would use a rewrite. And the cube root can be written as a 1/3 exponent. Now that we have an exponent, we can do the derivative, y prime. By the way, just a side note, that would be dy. And no, it's not dy dx, it would be dy dt, because it is the derivative of the y function with respect to the variable inside, in this case, the t variable. And the derivative, well, that's a power rule. We bring the power down, and then once again, we subtract 1 from the exponent. Subtracting 1 from 1/3 is a negative 2/3. Please, if you're going to use your TI calculators to do this, make sure you get very friendly with the math fraction option that turns all decimals into fractions. So we get negative 2/3. And yes, once again, I will want you to clean up nicely. And to clean this up, all it really means is to take the negative exponent, and that allows you, using exponential rules, exponent rules, to make it a 2/3 power. So my derivative is really 1/3 t to the 2/3 power. Cool. So we just talked about radicals. Please keep those in mind in advanced videos. All right. We also, every now and then, come across expressions like x squared over 10. And we need to take its derivative. Now, that is a fraction rule, and you'll learn about the fraction rule later. But once again, this video, the theme of this video, is all about rules from algebra. And we have this rule from algebra that says the numerator can always be maneuvered, and I can't say that word, maneuvered off top to make the expression 1/10 x squared. The reason this works is because if you put x squared over 1 and multiply, it'd be top times top over bottoms times bottom. And that's why this rule works. But if I look at this, I go, ooh, this is nothing but, when I want the derivative, this is nothing more or less than the power we've been using. 2 times 1/10. Well, 2 times 1/10 is 2/10. We always reduce our fractions, and that's 1/5. Again, 2 down to multiply is 2/10. 2/10 reduces to 1/5. Please subtract 1 from the exponent, and there's your first derivative. All right, let's see this again in another example. So let me bring out the function notation. F of x. If you have a function f of x, and your function is something like 7x to the 8th over t. And of course, just for giggles, let's add a 10x to that. All right, so there's my function, and I want its derivative, all right? So I want the derivative of this. So we write f prime of x. So how do we take the derivative of this? Well, here's what I'm going to do. I'm once again going to split it into two problems. The derivative of 10x, no big deal. The derivative of 10 times the variable is always 10 because of the linear rule. That is 10x, this is a line with slope of 10, and that's why the derivative is 10. Remember, the derivative is the slope. All right, over here. Now here, I run out of room a little bit. I'm going to once again kick the x to the 8th over here. The x to the 8th will come over here. Will allow me to do a power rule. So really what I'm going to do is take the 8 and multiply it by 7 to get 56 over 13 to the 7th. Again, just like this rule right here, I kicked the x squared off top. I'm going to do it here. I'm going to kick the x to the 8th right there. And then 8 times 7 thirteenths is 56 thirteenths x to the 7th. And don't forget my plus 10. Because whenever you have a plus or minus, you may split your problem into separate, smaller problems and use the power rule, the linear rule, and of course, up above, the constant rule. Excellent. We're doing a great job here. Last but not least, my third thing. So we have the radical rule. We have what if we have a constant in the bottom? And so what if we have a constant in the top? So let's say we have 13 over x to the 4th. How would we take the derivative? And of course, just, sorry, let's not go too fast. Let's say we want the derivative of this. Well, this, once again, my friends, is algebra. What we would do is recall, if you have a single term in the denominator, that's called a monomial, a single term in the denominator, you can bring that expression up to the numerator by negating the exponent. Again, rules of algebra, rules of exponents play a huge role in calculus. Calculus is nothing more than algebra. You just got to get really good with your algebra rules. The derivative, g prime of x, and of course, our fancy notation, dg over dx, because it's the derivative of the g function with respect to the variable x, dg dx. That derivative, well, now that we wrote it like this, no big deal. I don't care what the power is. Let me summarize. I don't care how ugly this power is. Bring it down to multiply. So 13 times a negative 4. That is a negative 52. And now, please be careful when you do this one. We're going to subtract 1, right? So let's pause here. Don't go too fast, too furious. Subtract 1, we get a negative 5. And so that is my derivative. Bring the power down to multiply and subtract 1 from the exponent. You will now note that I'll do one more step, the cleaning up of this derivative, by bringing that negative exponent back down. And so what I have is negative 52 stays up top. That's really a times between them, and that allows me to drop the exponent to the denominator because there's actually a times in there. So that negative 52 stays in the numerator because that doesn't have a negative exponent. It's only the x that has the negative exponent, and that's why that is the only term that drops to the denominator, in case you're wondering. Once again, I'm really utilizing the derivative rules and the exponent rules together for this. So I thank you for watching the basic derivative rules, and we will be utilizing these in the advanced rules to come. Thank you.